We're talking about an example related to multiple linear regression. And it is an example from the Anderson textbook. It's an issue near and dear to every university's heart. What drives alumni giving? Okay, so we are thinking about what drives alumni giving, and we have some parameters, some variables. One variable is graduation rate, and that'll be expressed as a percentage. The other variable is percentage of classes under 20, and that'll be, of course, as a percentage as well. The thinking graduation rate, right? Quite probably, more likely to graduate, more likely to become alumni, more likely to donate. Students who don't graduate tend not to donate money back to the institution. The thinking with smaller class sizes is smaller class sizes, you get to know everybody, you get to know your classmates, you get to know the instructors, and therefore you bond more with the institution. I think there's certain validity to that. And so we'd expect that to be positively related to alumni giving. The student-faculty ratio, same kind of idea, right? The more, this one would be a little bit negative, right? The more students, so if we think of student-faculty ratio, that's student to the number of faculty. So as this number gets bigger, there's more students for every instructor, and so the thinking would be that, okay, you don't really bond to the university as much, and therefore as that number gets bigger, you're less likely to donate. So that relationship we'd expect that to have a negative relation. It would be negatively related. Now we run the model and we see what's going to happen. So in essence, when we write the model, population model to be estimated, we don't even need any output. We don't even need to have gathered any data. We just have a sort of a brief action plan as to what we want to do. Okay, and our brief action plan that we want to do is we want to predict alumni giving. So we want to predict alumni giving. Okay. And that's going to be a model, so it might be per individual, and there'll be an intercept plus a first coefficient, but then we have a name for the x now, grad rate for a particular student, plus beta 2, again, Greek letters, okay, and we just call this, I'll just call it under 20, and you'll sort of want to make it somewhat easy to relate to, and then plus beta 3, the student-faculty ratio, and then plus, because it is at the end of the day a model, not an equation, so we have a little epsilon. Okay, so we sort of have, this is sort of our action plan. This is what we're trying to estimate. We're going to try to figure out what alumni giving percentage is based on these three parameters and an intercept. Part B requires us to actually run the regression, to get output to write the estimated regression equation out. So to do that regression, and in the lab, they'll go through the details of this and give you a little bit more guidance, and you'll do some more hands-on examples. This one I'm just sort of telling you, I'm just projecting it out there in a one-way form. And so there is under the data analysis tab. So if you when you open up Excel, you'll see the data analysis. In that data analysis set of tools, there'll be very many tools in there. And this is sort of where you went to find your descriptive statistics, etc. earlier on in this course, as well as in your previous stats course. And so we'll select regression. Makes sense. We're doing regression. A couple of things to remember. I mean, really, it's just filling in a dialog box. But before we get that far, the X data, the independent data, this is just particular to Excel, must be as a single block. Must be all bunched together, right? X1, then X2, then X3, then X4. So when we look at how our data would be arranged, we would have, because we have designated X1 to be graduation rate, X2 to be classes under 20, X3, let's say just the third parameter to be student-faculty ratio, we would want those three columns of data to be together, and it'd be graduation rate, then percentage of classes under 20, then student-faculty ratio. Okay, so you keep them in a certain order. The Y theory can be anywhere, right? Often it's together with the rest of the data just so that the sheet's not messy, but the Y doesn't have to be connected to the other X's. Okay, so this is very important. And so we pull up that regression tool, and we have an input for the Y's. So alumni giving, right? There's our input. And again, it can, in theory, can be anywhere. And then we see we have graduation rate, percentage of classes under 20, student-faculty ratio, all together, grouped together from where we want X1 to be to X2 to the X3. Labels, they're not mandatory to do the math, but they're pretty doggone convenient, okay? Because when we get this output out, the last thing we want is these sort of generic kind of labeling and that kind of thing. So we like to have some sort of name to it, both so that it's easier for us to look at, and secondly, easier for the client who may look at this later to figure out what it is that you were doing. Also, sometimes as a practical matter, the time from when you actually do the data to when you present it to when you write the report. I mean, in academia, in the class, it's fairly tight, right? You do the data, you write the report, boom, you do the presentation, bing, bing, bing. Sometimes in reality, there could be pretty big gaps, blocks of time between it, because it's just not convenient for the client to really look at it. And so you do the report up, and then it may be a month before you do the presentation. It's awfully nice to be able to go back and look at your work and remember what the heck it is that you were doing. Because in the moment, it all makes sense, it all flows, and then you get a block of time between finishing it and then presenting it. Oh boy, you really, really appreciate when you use parameter names that are easy to reinterpret. It all comes back to you, but you really want it to be easy to reinterpret. So labels are important. We avoid constant to zero. It's a possibility, but it introduces R-squared problems if we do that. And so we usually don't touch that button unless there's just an overwhelmingly compelling reason to do so, which there rarely ever is. We select the output range. We can put it on the same sheet, which is what the first choice is. We can put it in a new worksheet, wherever we like. Okay, put it in a completely new file if we want it. The residuals, which we will use in residual analysis, there's our choices there. Right? And as we saw in the simple linear regression case, that simple matter of the errors, just the observed y minus the y hat, there's a lot of information and diagnostic power in just that simple relationship. We will use the normal probability plot because that's a very easy way to verify normality. Remember, one of our assumptions from the simple linear regression case is that our errors are normally distributed. And if our errors are normally distributed, the y, the observations, the dependent variable, is also normally distributed. Okay? So that's an easy way to verify it. There are tests for normality, and the situation that you face in the future may require you to conduct one of these tests, and then just recognize the tests are available, and then you'll have to do some self-learning to figure out what they are. Most of these regressions are fairly robust to lack of normality, kind of, sort of. Right? All right, so we spit out our data, and we got this, right? And it looks very similar to what we would have seen in the in the simple linear regression case. Okay, so this is our Excel look at the data, and this is if we see it in R. Okay, so you are likely to at some point encounter, if you do quant or do modeling, the statistical program R. Doesn't hurt to kind of have an idea of how it's arranged. It's an open source statistics package, so maybe doesn't have quite the nice glittery front end. In fact, this is the glittery front end of it. So it's maybe not as pretty. So maybe a little bit more statsy, a little 90s feel to it, I guess, in the way things are arranged. But all the basic information is still there. This program is cheap. So when you start, it's cheap as in cheap. It's zero. You can do a lot of powerful statistics on R that you can't do on Excel. So it doesn't hurt to know that it exists at the very least. So anyway, we'll look at the pretty output from Excel. And we have all our basic attributes. There is a R squared. Adjusted R squared is going to be our go-to. Okay. Now we'll talk a little bit later about what it's adjusted for, but its interpretation is the same. Okay, so adjusted R squared that we see here, we see it's 0.679. So 68% of the variation in the percentage of alumni giving is explained by this model. So very boilerplate language, but very important language. Okay, so we have our adjusted R squared. Standard error of the estimate's just sort of like it was with the simple linear regression. How widely distributed the dots are about the line. So any particular forecast for the percentage of alumni giving, we would expect that particular estimate to be plus or minus 7.6 percentage points, 68% of the time, plus or minus 2 times that, a little over 95% of the time, and so on, using the empirical rule. We have 48 observations. And in the middle here, we have our ANOVA, right? And we saw that was just our testing table for, is the model significant? Okay? And we'll get into the details as to the structure of that particular F test in a little bit, towards the end of this unit. Okay, but there it is. We see, that's a very small p-value. So whatever it is that HO is, probably rejecting it, right? F-stat has its degrees of freedom, 3, number of parameters. Right? Before we only had 1 parameter, now we have 3. And then the residual, the error degrees of freedom, which we'll get into the details of how that's calculated a little later on. For now, we have our model, and so there's our estimate. And so we can look at our estimated equation and see that it's alumni giving, and I'll use the hat. I could use the expected value. So alumni giving hat, and we have particular estimates equals to minus 20 point. I'm going to round this a little bit so we're not writing so much. We can always look up the exact numbers later. Minus as our intercept, plus 0.75 times by the grad rate, plus 0.029 times by the under 20, and then lastly plus, minus, right, we were expecting that, 1.19 times by the student faculty ratio. Right? We were expecting that negative. Okay, so there's our particular line, and we can interpret that line. Now I'm just going to refresh a couple of ideas behind that interpretation, just in case there's been a block of time between you looking at this and you having finished a simple linear regression. So with the estimate or the interpretation of the intercept has meaning if all the x's, every single one, grad rate, under 20, S divided by F ratio, if all those are equal to 0, minus 20.72 is the percentage of alumni giving. Now we ask ourselves, before we even get to the interpretation of that minus 20.72 number is, well, first of all, couldn't the number be minus 20.72? Right? Does that number itself have any practical meaning? And you start to think, negative percentage of alumni giving, what the heck does that look like? And you go, that makes no sense, right? Less than the alumni are giving money. What do you mean? I could see 0% of the alumni giving money because they really hate the institution. Nobody gives money. Maybe I could see 20% giving money. But how do you get minus 20%? They take money away? Yeah, even that doesn't make sense, right? By the way, we're not refunding any of your tuition, right? So you kind of suspect that even if that were the case, it couldn't be the case. So in and of itself, the number minus 20.72 has no practical meaning in this case, right? The statisticians might go, ooh, interesting. Ooh, there's the number. Let's test to see if it's significantly different than 0, and go on and on and on and on. And we go, a number has no practical meaning. We really don't care. Let's move on to things that are important. The second thing that we could look at is, could all those x's be 0, right? Even if, big conditional here, please underline it, put asterisks around it, even if minus 20.72 was a number that had any practical meaning, could the grad rate and the under 20 rate and the student faculty rate ratio all be 0? All be 0. Well, let's look at it. Could the grad rate be 0? Nobody graduates from this institution. I guess theoretically that's possible. I don't know how long you'd last if you did it that way, but theoretically that's possible. Could you have, could it be theoretical? I mean, if you had, let's think about it, right? Theoretically it's possible, but if nobody graduated, could you ever have any alumni? Probably not, right? And so under 20, could there be no classes under 20? Okay, fair enough. Maybe there's not. Student faculty ratio is 0. Well, if the student faculty ratio is 0, the only way that happens is if students are 0. Well, heck, if there's no students, there's going to be no alumni, right? You're bankrupt. You're an institution with no students. Guess what? There's going to be no alumni. So even that, no practical way that grad rate under 20 and student faculty ratio are all equal to 0. So in this case, the intercept has no practical meaning. Okay, so that's important to us. Oops. Okay, and so we could also, if we're in any doubt, we could always look at the raw data on the spreadsheet and see if there's any cases where all three were equal to 0. Okay, if we're really unsure, and right now I don't think we're unsure, but if we were unsure, we could then check the raw data. That's always open to us. Okay, so now we have those three other coefficients. We have the coefficient for grad rate, we have the coefficient for under 20, and we have the coefficient for the student faculty ratio. Now, can we interpret those? Well, absolutely. A couple of things to keep in mind is we look at each particular coefficient in isolation. So we hold everything else constant, right? Ceteris paribus, if you remember from Econ 101 and 102, you see that Latin phrase all the time. Just means everything else staying equal. So we're only going to look at one coefficient at a time. Now, we look at that one coefficient at a time, we go, okay, if that particular variable goes up by 1 unit or goes down by 1 unit, that coefficient represents the average change we would expect. I'm double using the word average and expect. It's a redundancy, but it's essentially becomes what we'd expect the change in alumni giving to be going to be, okay? Or what the change in alumni giving would be on average. So, for instance, when we look at that coefficient for grad rate, that means that if the grad rate increases by 1 percentage point, right? Alumni, let's see if I can write this. Alumni giving increases by 0.75 percentage points on average. Okay. And we can then we could say a -2, but it's negative numbers tend to be a lot clunkier to work with. Same thing is we can go and look at the under 20 rate. Okay, so if the percentages of classes with under 20 students, if that goes up by 1 percentage point, okay, alumni giving increases by a little bit less, 0.29 percentage points, and again, on average. Okay, and we can extend that to the student-faculty ratio. If the student-faculty ratio goes up by 1, okay, we would expect, or on average, the percentage of alumni giving would go down by 1.19 points. So if the student-faculty ratio, let's say, was 20, and it went up to 21, we would expect student alumni giving to go down by 1.19 percentage points. Okay. So all very important things. So if you want alumni giving, you want to keep that student-faculty ratio as low as possible, and the next biggest thing would be the graduation rate. You want to ensure that students graduate but meet the qualifications, right? And that's where good teaching, support systems, all that kind of comes into play. Right? You can't just giving away degrees. Well, that increases your grad rate, but of course it diminishes the value of your degree, and diminished degree means lower job opportunities. So when we start to think of what other factors might be missing in this alumni giving model, it could be percentage of graduates who get a job within the first some segment of time, and so on, right? So average income of a graduate and things like that could also be in this model, right? So the fact that we've got these three started out doesn't mean that they're the only three. We can look at the output. We can see there is some unexplained variance, right? If we say it's almost 70% of the variation in alumni giving is explained by this model, there's also that 30% that's not. And in that 30% could be the job variables related to the job prospects of the graduate. Okay, so let's keep that in mind. There could be other issues here as well. Okay, we come back to our next segment. We'll talk about this R squared and its adjusted version.